Hello YouTube, Tristan Taylor here. Today I'm going to read a couple more pages of Power Station Operation 3rd Edition. Let's get to it. Alright, let's see, second page of chapter 1. It'll be up on the green screen again. Okay. Resistance can be defined as the element in an electrical circuit that limits the flow of current in the circuit. Electrical energy flowing in a circuit containing resistance is converted to heat energy proportional to the square of the current flowing through the resistance, or in other words, energy consumed in watts in a circuit containing resistance is equal to current in amperes, squared times resistance in ohms, or power consumed equals 1 squared RW. The behavior of a circuit containing only resistance is shown in figure 1-1A, which will be somewhere here. The resistance of a circuit is affected by the resistivity of the material conducting the current. Resistance varies inversely with the cross-sectional area of the material and directly with its length. Most metals are relatively good conductors of electricity, that is, they have a low resistivity. Other materials such as dry wood, glass, rubber, and many plastics, and porcelain have very high resistivities. That is why, because spark plugs run at very high voltage, so this is why they have this like ceramic or porcelain insulator on it, so that this stays separate from this. So other materials such as dry wood, glass, rubber, and many plastics and porcelain have very high resistivities and are classified as insulators. Liquids and gases may have high or low resistivity depending on the temperature and various other factors. Pure water, for example, has a relatively high resistivity, whereas water with salt or many other chemicals dissolved in it is a relatively good conductor. Many liquids, particularly acids and salts, are good conductors, while many petroleum-based products or liquids are good insulators between certain temperatures, but may become conductive at high temperatures. In fact, carefully refined oil is used in transformers primarily as a coolant, but it also has good dielectric properties and can be used as electrical insulation in some applications. In fact, the example I give here of it being used as coolant is they put mineral oil in ignition coils for engines. So, for example, they'll have, you can shake your ignition coil. It's like a cylinder, and there you'll hear fluids flashing around in it. That is mineral oil to cool it, to help it keep cool. There's always some resistance in a circuit, perhaps only that of the circuit leads and the internal resistance of the battery or other power source. Note, there is one exception. At very low and specific temperatures, some materials exhibit zero resistance, called superconductivity. However, this is a special case, not ordinarily encountered in normal circuits. Inductance. Inductance can be defined as the element in an electrical circuit which opposes sudden increases or decreases of current flowing in the circuit. Inductance stores energy in a magnetic field when current is increased and delivers it back to the circuit when current is decreased. The amount of energy returned to a circuit would exactly equal the amount of the energy stored if there were no other resistance losses in the network. The effect of inductance is to delay the changes of current. Figure 1-1B shows the effect of inductance and resistance in a circuit. After the initial closing of the switch which supplies the battery DC voltage to the load, the current increases exponentially and to a maximum limited by the resistance in the circuit, and will maintain this value until the switch is opened, when it will begin to decrease exponentially. In an AC circuit where the voltage is continuously changing, consequently the circuit will also change, but at a time somewhat delayed, because an inductance will oppose a sudden change of current. As a result, the current in a circuit containing an inductance is said to lag the voltage. One complete cycle is 360 electrical degrees, and in an AC circuit with pure inductance, the current will always lag the voltage by 90 degrees. Practical circuits will always contain some resistance, so that in such a circuit, current will lag the voltage, but at an angle of somewhat less than 90 degrees, depending on the ratio of resistance to inductive reactance. Coils of a conductor are primarily inductive, but always contain some resistance. The amount of inductance is proportional to the number of turns in the coil, the diameter of the turns, and to the material used in the core. Magnetic materials such as iron greatly increase the inductance of a coil compared to one with an air core. Straight conductors such as transmission lines also have inductance proportional to the length of the line and spacing of the conductors. This factor is important in determining the behavior of long transmission lines. Okay, that concludes today's video. I want to thank you guys for watching. Peace out.